All right. Oh, okay, 1 second.
Hello.
Okay, I'm going to try this again. Hello, hello. All right, cool. No echo this time around. That's great.
Awesome. Can you hear me all right?
Yes, and I think you can hear me okay as well?
Yes, I can hear you great.
Great. Awesome. So we've got the audience coming in from the previous session about Eclair, and now we're moving on with Sebastien, who is a ZK researcher, talking about Plonky2. Sebastien has, been an invaluable educator in my own journey on understanding zero knowledge proofs. I don't know, Sebastien, if you remember our little session in ETHSF, sitting at the tables waiting for everyone to judge some hackathon prizes. But yeah, learned a lot from that session and really appreciate it personally. So I'm really excited to see your talk today and learn a little bit more.
Awesome. Yeah, thank you. Thank you so much for the intro, and thanks for coming, everybody. So today today we're going to be, considering Plonky2. And what that means is we're not going to be diving much into the details of how it works. But what we will be doing is talking about some of the high-level information that an engineer who's considering it, whether or not they want to use it for their project, might want to know. And that includes things concerning things it's good at, things it's bad at, what situations when it's good, situations when it's bad, and then a brief comparison to some alternatives. So its quick overview. Plonky2 is a Plonk-ish proof system, and so that means you have all the things that Plonk gets you. It means custom gates. It means custom polynomial arguments like lookups or what have you. It's also, unlike a lot of the other Plonk systems, built atop Fry. What that means is that instead of elliptic curves, we use hashes, which, as we'll explore later, also exploits some interesting trade-offs. But one of the things that we care a lot about that we get from Fry is the lack of a trusted setup. That means it's transparent. Now, performance-wise, it gets its performance from using a small field, a 64-bit field called Goldilocks, which is small enough to fit in a single CPU register. And the multiplications are much, much faster, 40 times faster, because they're much more friendly to modern hardware. Now, that's all fine and dandy, but the most unique thing about Plonky2, and this is something we'll also be exploring a little bit here, is the tiny recursive verifier circuit. And what that allows is proof recursion is fast and practical and even easy enough that it's a viable and valuable tool for building whatever your application provides. So bundled inside Plonky2, there's actually two proof systems, not one. There's Plonky2, and then there's also this other thing called Starkey, which we'll be talking a little bit about. Now, there are two proof systems that we can use recursion to compose inside of each other. And they're both good at different things. Plonky2 is a SNARK, so that means you're writing circuits, right? So we have a diagram here where you might have kind of an arbitrary structure for your computation. Well, as Starks are kind of repeated state transitions. So they're only good for the kinds of computations where you're doing one thing after another after another. And so there are a lot of computations that fit better in a Stark and better in a SNARK. And what Plonky2 kind of allows you to do is you can use both whenever your application needs it. Features. So now let's move on to features supported by the two libraries. So Plonky2 currently supports zero knowledge, supports custom gates. So if you need a custom gate for whatever application is, you can just kind of implement it. It supports recursion, both your typical like recursively verifying another circuit, but also a sort of cyclic recursion like Mina. it can do that. It also supports random access. So if you have an array of elements, you can look up from it. So that's like similar to a kind of lookup table, but it's not exactly the same. And then it also has a bunch of basic gadget libraries for things like integers, big number arithmetic, and the elliptic curve that Ethereum uses for its signatures. Now, Starkey is more of a very minimalist. Starkey is more of a minimalist example that you kind of have to fork. So it doesn't really support any examples, but it's a really fast Stark implementation, and it's really good at what it's good at. Now we can move on to the thing that a lot of you have probably heard about. It's performance. So performance for Plonky2 is, well, pretty good, albeit with some larger proofs than you might have seen elsewhere. Some very rough numbers here. We'll share the slides after, and you can see some more performance tables where you run it on different sizes and whatnot. But roughly, Plonky2 can prove over approximately 2.4 million trace cells a second, and Starkey around 12 million trace cells a second. Now, adding zk adds some overhead, and so in Plonky2 in particular, it adds more overhead than in other proof systems, so that's something to watch out for. Now, an interesting thing that Plonky2 offers from a performance perspective is the ability to tune the Frye polynomial commitment. And what that means is that it gives us a sort of knob that we call the blow-up factor. And the blow-up factor is essentially this thing that if we increase it, we get a 2 times faster, or we get a 2 times slower prover, but we also get smaller proofs. And the opposite is true too. If we decrease it, we get a 2 times faster prover, but a bigger proof. And the cool thing is that we can sort of choose depending on what we're doing. So if we're proving a small circuit, we might want the smaller proof, and we can be okay with a slower prover. If we are proving something really big, like say a zk EVM, we can turn the blow-up factor all the way down and get a really fast proof. And this really feeds into the flexibility that Plonky2 provides, and that the ability to use recursion as just a standalone tool. It's not something that's like a big effort. It's not something that's really expensive. You can just sort of add layers of recursion. Is now what you can do is you can separate different layers of proving for sort of different things, right? So we have a diagram here that Remco made. He's the CTO of WorldCoin, and we can, we can have a really big proofs with a fast prover, and we can prove, say, lots of our big statement. We can even break it into chunks, right? And then what we can do is we can use recursion to verify the big proofs that we proved fast in a small proof, right? So now what we've basically done is we get the best of both worlds. Is we get fast prover and a big proof, and then we wrap it into a smaller prover, a smaller proof with a slightly smaller, we wrap it in a smaller proof. So we can basically say one place we prove the statement that's big, one place we make the proof small. And we can even actually do this to add other properties. For instance, we can add zk. We can switch to a different hash function. We can switch to a different finite field even. We can even switch to a different proof system, as there's actually an experiment going on wrapping Plonky2 inside Groth16. Now, performance is great, tunability is great, flexibility is great, but it does come with some drawbacks. One of them, and perhaps the biggest one, is that Plonky2 uses a very small field. Right? And now, in a way, this kind of gives it the performance. This is what it's great for. But it also means that sometimes it takes more field elements to express the same computation than you might use in, say, you might be able to use in a different proof system. Now, for a lot of things, this isn't necessarily the case, but there are a lot of tricks that you might want to use that you just can't use in Plonky2 because it will overflow the field. This also means non-native arithmetic, right? Like say doing ECDSA signatures, for instance, is less efficient because now you need more field elements to represent, say, an elliptic curve for signatures that Ethereum uses. Another weird thing is that a lot of proof systems and other curves have an embedded curve. So for instance, Groth16 has baby jub jub that allows for efficient elliptic curve arithmetic inside the circuit. In Plonky2, we don't really have such a thing because to have a secure curve, you need a bigger field. And so there is like a workaround, but it's a bit odd because now you have to work over, but it's a workaround and it's a little odd and it's a little awkward. So you don't have something that's really clean like baby jub jub. Now for usability, the library itself is very clean. It's low level, but it's very clean and simple. You kind of just given a builder pattern and you can, and all the wiring and the locations and the offsets are kind of abstracted away via targets. And so this is something that, you know, if you're working with Groth16 or CircCom is definitely handled for you, but maybe something like Halo 2 or something like Halo 2 might not, kind of exposes some of these details for you. You kind of have to think about the layout of your circuit a little bit. It also comes with some ready-to-use gadgets, as I said, for recursion that allows it really easy. So you can just call a dot recursively verify proof function, and then then it's done. So it's pretty easy. And I have some code example here, kind of running a little bit low on time. No, I think we're all right. So to write a Plonky2 circuit, it's actually very easy. So what you do is you kind of first you set the circuit config, and you basically say, okay, I'm saying what hash function am I using, what field am I using, and also saying a bunch of other things like how am I setting the fry rate, which I'll show how you actually set that in a minute. And then you kind of wire up your constraints using the builder. Then you say which values in the circuit are public inputs. You load them into a witness object, which is basically how you say when I'm going to prove, here are the values I'm putting into my public inputs. And then I build the circuit, and then I prove. Then I'm done. Right? And all in all, this is about like 30 lines of code for, it's a basic circuit, but the actual setting up of the circuit is a very small amount of code. And for reference, it took Brandon, the CTO of Manta, around like a few hours to actually build a prototype backend for OpenZL over this interface. So it's very friendly to compiler infrastructure. It's just very simple overall. Now, this is not as important, but it also shows that there's a config that in this sort of, so if you go back here in step 2 where you set this config, so you can actually modify a field in this config called the fry config. And here you can set a parameter called the rate bits that allows you to sort of tune what your fry blowup factor is. And so it's as easy as just setting a single variable. And you can set this thing, you can turn it down and make your prover fast, but your proofs larger. Or you can turn it up and get the opposite effect. Now, on the other hand, Starkey is a little bit awkward. Starkey is kind of this low-level, minimal example. Writing Starkey circuits, not really circuits, but writing Starkey programs is it's almost like writing assembly. You need to, and oftentimes you actually need to fork the library to add extra functionality that doesn't come baked in. So Starkey is from a roadmap perspective, there's a lot of improvements, and in fact there's some improvements in store actually working on top of OpenZL that might be coming in the future. But there are some examples, and we'll share the slides later so that you guys can go and check out the code examples to see what it looked like, but it's pretty awkward. So that's something to consider. So if you do want to use Starkey to get the maximum performance, you might not, it's probably not very straightforward unless you have a lot of the cryptography background. Now, perhaps one of the most important things to consider when deciding whether to use some developer tooling or important library in your stack is ecosystem. And well, for Plonky2, well, it's a pretty new proof system. Halo 2 has been around longer. Halo 2 has been kind of open source longer. Halo 2 has the support from the Ethereum PSC. It has support from there's these hardware acceleration companies building on top of it. And it's not to say that Plonky2 doesn't have hardware acceleration companies looking at it, but there's definitely much more of an ecosystem building around Halo 2. So if that's something that you care a lot about, then Plonky2 might not be the best choice. However, the Plonky2 ecosystem is starting to pick up. We have a lot of gadget libraries built out of the box, but there's actually some more that are being built kind of as we see. We have some curve gadgets for both Ethereum signatures and the ed25519 signatures, which is what Near, Solana, a lot of the other blockchains use. We have some big gadgets. We actually have some gadgets that mimic like dynamic arrays. We have some, and there's a lot of interesting gadgets coming in the future. Tooling wise, there's actually a prototype by Polymer DAO, which is they're a cool company building a zk bridge. Check them out. But they are building a CIRCOM wrapper for Plonky2, and so that means is that you can actually go from a really fast Plonky2 proof to the minimum tiniest Groth16 proof, and then eventually put that proof on Ethereum. And so this is something in progress, but it's a really cool experiment that you will be able to do soon. It's open source, so we'll be able to do that soon with Plonky2. Now, don't have much time left, but I'm going to do a quick, high-level comparison between the alternatives. So I already talked a little bit ecosystem-wise. Plonky2 definitely loses out to both Halo 2 and Groth16, which I think are the main alternatives to what an engineer is going to consider. Now, concrete performance-wise, at like a raw performance, it's not as great. It's very good. Other proof systems might not be as good. Versus Halo 2, there's a lot of lookup tricks that Halo 2 might be able to do in different circumstances, so it's not as clear a comparison for Halo 2. But one of the main things that Plonky2 does have, I would say, in comparison to these other proof systems, is you have the option to just add recursion if there's something that you need, and adding that to your main circuit is going to make it really slow or cause a lot of headache. Whereas instead, you can say split it up into 2 steps. For instance, maybe adding zk to some circuit will make it twice as big and make it twice as slow. So you can instead kind of look at it and say, well, instead of doing that, I'll prove it without zk, and then I'll wrap it in a recursive proof that has zk enabled. And now I have a proof with zk. And this kind of allows you to write your code in a way that kind of separates concerns. Now, just like Halo 2, it has no trusted setup, and it doesn't have any circuit-specific trusted setup either, which Groth16 does have. Other than the ecosystem thing, Groth16 also has CIRCOM. Halo 2 and Plonky2 don't really have anything like that. You just kind of have to use the library to write your circuits, and then kind of hope that there is tooling that allows you to, say, wrap it up into a web app, which Groth16 has, or at least the CIRCOM has. You have this tooling that allows you to go from, called SNARK.js, that allows you to go from CIRCOM to circuit. I'm proving it in a web app, and I'm verifying it on chain. The tooling for Halo 2 has like some prototypes for that, but it doesn't have anything as robust as Groth16. And then Plonky2 has nothing of that sort yet. Yeah, hopefully that's I know I'm like out of time, but that's a rough overview of Plonky2. I know there was a lot of information, but hoping that was helpful.
Awesome. Thank you very much, Sebastian. Really appreciate it. Yeah, unfortunately, we're out of time, so we can't really take any audience questions right now, but that was a super helpful presentation, comparing Plonky2 as well to a few other alternatives. And so next up, we're going to be going live with Brian from